Though it has absolutely nothing to do with neutralization reactions and titrations, redox reactions are an important thing we must understand to get to grips with acid plus metal reactions. So let's take a look at redox reactions. So what does this word redox mean? Well, it's a portmanteau of oxidation and reduction, first introduced in 1928 by Leonor Michaelis and Louis Flexner. It used to be that this was the word you describe to any oxidation or reduction reaction, but now we realise that the same mechanism is taking place whenever electrons are being transferred. To get to grips with redox reactions, chemists invented the oxidation number, which is a theoretical number that you would get as the total charge if all of the bonds that an element could form had formed, making the assumption it was 100% ionic and that the electrons were all assigned to the more electronegative atom. Then you would have a total charge of this, and we call this the oxidation number. Now, any element bonded to itself would have an oxidation number of 0. So, for example, hydrogen bonded to itself, 0, oxygen, 0, and the same with things bonded with metallic bonding, such as sodium or iron, would all have an oxidation number of 0. It gets interesting when we look at ionic and covalent compounds. So let's take a look at these elements or ions that might be involved in a compound. Now, to start with, we've got some elements by themselves, oxygen, hydrogen, fluorine, and what you can see is they have an oxidation number, -2 + 1 -1. Where does this come from? Well, we need to consider what the arrangement of the electrons in oxygen is. It has space for 2 electrons in its outermost shell before it has gained a full outermost shell, and has an outermost shell structure that is like a noble gas, which is ultimately the most energetically stable form it could have. If it did accept 2 more electrons to fill those shells and form 2 bonds in the process, it would now have a charge of -2. And so that is its oxidation number. You can also see and always imagine that in the form of water, H2O, oxygen has 2 bonds to form, and it will accept the 2 electrons from the hydrogens, and -1 from each one would give -2. So you can kind of see how it works from the formula as well. And that same logic applies to all of the rest. Hydrogen gives its 1 electron, so it's got +1, and having given it to the other species, then it is going to be missing one of its only charge, and so it would have gained a charge of +1, and so that's its oxidation number. Now, with the ions slightly further down, the sodium plus ion, the potassium plus ion, well, that's quite easy to figure out because the oxidation number is always the amount of charge on that particular ion. So that you can see that sodium plus has an oxidation number of +1. It means it has 1 electron to give, and in things like sodium chloride, it has indeed given that electron to the chlorine. It's quite straightforward, but it takes a little bit of thinking about before you can become very quick at this. So it's worthwhile experimenting and having a go. Let's look at something a little bit more complicated. How about sulfuric acid, H2SO4? Well, we know that those hydrogens have both got an electron to give, and so once that has occurred, they would both have a charge of +1. So the oxidation state of the 2 hydrogens would be a +1 and a +1. The oxygens, however, they would each have space for 2 electrons, would receive 2 to get full outer shells, and so they all have an oxidation state of -2, and there's 4 of them, meaning there's -8 in total as the total charge. What would the sulfur have to bring to this formula to make it a nice balanced out thing? Ultimately, we want the charge on this to equal 0, so sulfur has got to bring to this an oxidation number that when you've added up all of the individual oxidation numbers would make the whole thing equal 0. So we've got 2 sets of +1 and 4 sets of -2. It means that the sulfur really has to bring a charge and an oxidation number of +6. So that's how we would work it out. And you can see here on the right-hand side, the how about these box asks you to work out, well, what would the oxidation number of the sulfur be in things like sulfur dioxide and sulfur trioxide, along with a load of other more complicated. It examples. But what you can see from the sulfur dioxide, the sulfur in sulfur dioxide, well, if the oxygen is -2 and there's 2 of them, then the sulfur is going to have a +4 oxidation number. But in the second one, there's 3 oxygens, which means it's going to have -6, which means sulfur must have a +6 oxidation number to make it equal 0. It means that the oxidation number of any given element isn't always the same. Depending on what it's bonded with, that number can be different. So let's take a look at some elements behaving badly, or at least differently, depending on the things you're bonded with. So oxygen in H2O obviously has to receive 2 electrons from those 2 hydrogens, which means that it would have a charge of -2, having had those 2 electrons, giving the oxidation number of oxygen in that case as -2, and it would be the same for calcium oxide, because the Ca2+ ion would bond with the O2- ion, and so the oxygen would receive the 2 electrons from the calcium, and therefore it would have to have an oxidation number of -2. There, in hydrogen peroxide, it would have to be -1 because there are 2 of them, and so they've now only got 1 electron each from each of those hydrogens. And in oxygen difluoride, then the oxidation state would have to be +2 because those fluorines themselves would have an oxidation number themselves of -1. So -1 times 2 would mean oxygen would have to have an oxidation number of +2. Now, hydrogen itself also misbehaves in similar sorts of ways. You can see in ammonia, the NH3, that for 3 hydrogens all producing an electron each, then the nitrogen is going to have an oxidation number of -3 and the hydrogens all +1. In hydrogen sulfide, it's exactly the same. The sulfur would have an oxidation number of -2 and the hydrogens each would have an oxidation number of +1 each. But in metal hydrides, it's a different situation. The oxidation number would have to be -1 because the sodium, for example, would produce or would give 1 electron to fill hydrogen's outer shell, so that hydrogen would be indeed receiving an electron in this case. So its oxidation number would have to be -1, and the same for calcium hydride as well. Now, understanding which of these oxidation numbers we are talking about in any given chemical, we use Roman numerals in the name. For example, if we were talking about iron being Fe2+, with the oxidation number of +2, then we would use the Roman numerals of 2, iron 2. And it's the same for iron 3, that is representing iron 3+, Fe3+, with an oxidation number of +3. In the past, all of these different chemicals had different names, and it was sometimes a bit of a minefield figuring out what we were talking about. There were so many naming conventions, it became quite complicated. For example, an NO2- ion would be called nitrite, but an NO3- would be called nitrate. And so very easily you could end up getting the wrong stuff and poisoning yourself. To avoid that, they have changed the naming convention to include the oxidation state. They now call it all nitrate, but give in Roman numerals the oxidation state for that particular ion. So, for example, the nitrite would be called nitrate 3, and the nitrate would be called nitrate 5. Now, this is in most situations, but there are a few chemicals that maintain their old-fashioned names just because they're so commonly referred to by those old names. Copper sulfate, for example, will always be copper sulfate. But in the modern naming convention, we would call it copper 2 sulfate. It's the same chemical, we're just being more precise about the oxidation number. Now, all nitrates are, if you see it on a bottle, they are the NO3-, and so they are essentially nitrate 5. Now, it might not say that on the label, but trust me, that is what it is. Originally, redox referred to oxidation and reduction, talking about whether or not a compound would gain or lose oxygen. But then we think about oxygenation. What would happen if something was oxidized? Well, basically it would cause a loss of electrons. You think about if an oxygen came to you, then its 2 empty valence electrons, your 2 electrons, would go into, and so you would lose electrons from you if you bonded with oxygen. It means oxidation is loss of electrons. And that's true whether or not it's a covalent bond or an ionic bond. So in a covalent bond, it is precisely that. It's your electrons going into the valence positions to fill up the outer shell of the oxygen. You lose your electrons in doing so. But even if you're going to form an ionic bond, like a metal oxide, then what's going to happen is you're going to lose your electron. It's going to go to the ion of oxygen, and it's going to do exactly the same thing, fill in its outer shell. It's just going to be that you're attracted not because of your shared electron, but because of your opposite charge. That is how ionic compounds are different to covalent compounds. But either way, you have lost your electrons in bonding with oxygen. It's always that oxidation is loss. And reduction is always the other way around. Think of the poor oxygen. It's always going to gain electrons no matter what happens. It is always reduced. That means we have a more precise and narrowly confined definition for redox. Oxidation and reduction can occur whether an oxygen is involved or not. It only requires that in oxidation the electrons are lost, and in reduction the electrons are gained. So let's take a look at an example where oxygen is not involved. We've got iron burning in chlorine gas. And what we can see here, we've got 2Fe plus 3Cl2 goes to 2FeCl3. This is indeed a redox reaction. If you consider the product here, the FeCl3 is made up of the Fe3 plus ion and the 3 of the Cl minus ions. Now, to make this make sense, let's look at this in half equations where we concentrate on each ion at a time. The two ion turn into 2 Fe3 plus ions, and because there's 2 of them and they're both given 3 electrons each, it means they have all lost together 6 electrons. So it has lost its electrons, it has been oxidized. Whereas the chlorine, of which there are 3 pairs, they accept the electrons to become 6 Cl minus ions. It has gained electrons, and so therefore the chlorine has been reduced in this reaction. Now, these half equations can be quite useful because it can help us to see what's happening to the oxidation number of the various different chemicals involved. If we look at the example from the previous slide, the iron turning into the Fe3 plus and giving off its electrons, well, to start with, iron by itself has an oxidation number of 0. And now we can see that in the form of Fe3 plus, we've got an oxidation number of +3. Now, that means its oxidation number has increased. And when the oxidation number has increased, we say that that is oxidized. For it to have increased and become more positive, it must have lost some of its electrons. Looking at the chlorine, again, it starts with an oxidation number of 0, and it ends up gaining charge to the point where it is now Cl minus. So each one of those has now got an oxidation number of -1. The only complication here is, yes, each chlorine has gained an oxidation number of -1, but what we must do is consider that there's now 6 of them. So the total oxidation number of the 6 Cl minus would actually be -6. And going to the top, because there's 2 iron 3 plus ions, each with an oxidation number of +3, because there's 2 of them, then it must have an oxidation number of +6. And so one of them is now +6, and the other one is now -6, meaning that the oxidation numbers balance to 0 when you consider the whole reaction. So with that in mind, have a look at the reaction below. Copper going with silver nitrate, forming silver and copper nitrate. What is the species that's been oxidized? What has been reduced? What is the total oxidation number change for the copper and for the silver? Let's have a look. Well, the copper is now bonded to 2 of those, so it's increased by +2. Each of the silvers has decreased by -1, but because there's 2 of them, it means the total decrease is -2. It means the copper is oxidized, the silver is reduced, and combined, there's been no net change in the oxidation number. Now, why should there be no net change? Is because, well, basically the electrons given by one are the electrons accepted by the other. It should always equal 0 when we have neutral products. Going back to our very first thought, why is redox in this chapter at all, is because it helps us to understand reactions between acids and metals, the fizzing reactions when a metal dissolves when you put acid on it. Well, if we look at hydrochloric acid as a nice example of this, we've got zinc added to hydrochloric acid, forms salt and hydrogen. The salt is zinc chloride. Well, look at the oxidation number of the zinc. It goes from 0 to +2 when it's bonded with two of those Cl minuses. And so it has basically lost its electrons and it has basically become oxidized. And that is true with all metal plus acid reactions. They are all for the metal an oxidation reaction. The acid, however, goes through reduction. It ends up giving over electrons. And you can see that that has happened because in HCl, the hydrogen there had an oxidation number of +1 because it was basically, it had its electron in the chlorine, but on separating, it's ended up bonding basically with itself to form hydrogen. Its oxidation number has now become 0. It has gained an electron in the process, and so that is what's happened. But it's gone from +1 to 0. If you go from +1 to 0, you must have gained an electron. +1 to 0 means you must have gained a -1 for it to have gone to 0. So even though it says +1 there as the oxidation state on the product, on the reactant, because it's 0 on the product, it must have gone down. It must have gained an electron to go down to 0. And because there are two HCl's, it must have gone down twice. It must be -2 as the total. -2 and +2 cancel out. And so it makes sense that the electrons given by one species were the electrons accepted by the other. And it's the same with sulfuric acid. There's an example just there, slightly more complicated, but it all works out exactly the same. In fact, it's a common thing of all metal plus acid reactions is that they are redox in this way.